Okay, so after having spread through the atria, like I said, and start, then cause the atrioventricular node to depolarize, you're going to want to move this electrical signal through the ventricles and get them to work together. So the optimal idea is moving it through the septum, right? And then coming up and around really simultaneously with these a massive amount of fibers that would spread out and maybe almost look like an upside down willow tree is what I always picture this as. Here's our trunk and then these just massive fibers. So cartoons and your big heart in lab just never do justice to this idea. And the idea is we want a ventricular syncytium. We really want all the cells pretty much depolarizing together, and therefore they're all going to begin the process of contracting together. All right, so from the atrioventricular node, which is the only way to pass it into the ventricles, from the atria to the ventricles, we go into, again, the AV bundle, right, which branches into a left and right bundle branch. Again, this should say AV bundle or bundle of His. And these are going to then split to the right and left side, conducting the action potentials down and to the apex and then back up through the Purkinje fibers. All right? And this network, the Purkinje fibers, are again massive, and they go everywhere into the myocardium, and they're really responsible for most of the ventricles depolarizing at once, which will result in the recording of the QRS complex. All right? Again, this is a rapid conduction, and all the muscles will basically begin to contract simultaneously. And that's why we call it a ventricular syncytium, syn together. All right? So this recording just shows you the changes in electrical voltage, millivolts, over this really brief time, all right? So, and this, of course, is due to the movement of ions, just like we talked about in AMP1. And I said these potentials differ in the contractile and the conductive. The conductive, again, are doing the spontaneous generation. The contractile are waiting to be stimulated by the conductive. So, again, the cardiac conductive ones, these nodal system, have no stable resting potential. So they never really get to this. They always keep changing, as this is trying to show you. And again, I don't see myself writing a test question on this. This is really very much an information for students, because it is a bit of a refresher from AMP1, but it is a good thing to know, because we do treat people with heart problems with a number of, calcium channel blockers are pretty common. So there's a slow, and this also illustrates, when there's a problem with electrolyte imbalances in sodium, potassium, why that can cause the heart to stop functioning. So slow sodium leakage channels are really what caused this change from about -60 to -40. And this spontaneous depolarization, which is what's happening here, because here's our threshold, right? So just because of leakage channels, triggers then voltage-gated, they are affected by a change in voltage, calcium channels, which open, right? So here we see this in red, and continue depolarizing, all right? And then this triggers, right, gated potassium to open, which causes repolarization. So we have this depolarization, again, up to about +5, right? They're not quite the +20, but +5. Triggers then the opening of potassium channels, which repolarize, and this is very, very similar. So the difference here, of course, is that we have this kind of, like I said, continuous leakage that we never come to a stable resting potential like we did in skeletal muscle, right? And then, like I said, once the potassium, voltage-gated potassium channels get to the negative, they'll close, and we see this reopening and repeat over and over and over again, all right? So the contractile cells, right, do have a stable resting potential, all right? So they are waiting, and then they have a rapid depolarization that occurs once we hit threshold, and of course they're going to be triggered by the conducting ones, And we note here a long refractory period, a period in which, again, we can't, so it's divided into an absolute refractory where absolutely will not respond, and a relative where if it's a high enough stimulus, it'll respond. Again, I really don't see myself asking these questions on a test because this is new and it's different from holes. But it's an important backstory, if you will, that shouldn't have been left out in holes. It should have been, there's some things that, no, you don't have to be assessed. You may not totally grasp it yet, but you have to be aware of it. All right, and this is what I'm talking about as a backstory. All right, if you want to think of it that way. So again, this rapid depolarization, very similar again due to sodium, right? So still this high extracellular sodium. Rapid depolarization that would occur once they receive the stimulus from the conducting cells, and then this slow potassium channels, which kind of keep the so you don't have this immediate repolarization like you tend to have in nervous tissue and muscle. So a slow calcium channels, again a high extracellular, so keeps the membrane charge reversed, right? And then so we call this a plateau because nothing's changing in this time period, right? And then they close, right? Again, it's a slow closure and slow opening, slow closure, and then we can repolarize. Again, same idea with potassium, as we've always talked about that, right? And during this long, again, refractory period, you can't initiate electrical changes again. And I just reinforced here, the plateau here comes from these slow calcium channels, and not many potassium channels at this time would be opening until we come back down to 0. So there's a requirement to start the repolarization. Right? Now, why this becomes really important, and again, like I said, while I'm not going to ask you, give me the details on this, this reminds you that we can't, right, we need these periods of time so that the heart can do its job, right? So where it's not changing its electrical potential so that the heart can actually functionally fill and move blood. Okay? We measure these changes that you saw through an ECG or an EKG. So we talk about the QRS complex and then the T wave. And what these are, again, is they're actually showing not the nodes themselves, but the atria, the atrial cells getting excited, changes in millivolts, and the ventricular cells getting excited, depolarizing, and then the ventricular cells repolarizing. So they track this pathway of change, electrical change through the heart, and therefore the success, what I say is a success, that the nodal system is working and spreading these action potentials which are stimulating the contractile cells. All right? So this shows you basically where you put the leads in a 12-lead system, though you can use as few as 3 in a crude EKG. All right? So depolarization waves, again, P wave, the P wave is atrial depolarization, and what we would see is the wave starts after the SA node has moved and rapidly moved, all right? The electricity from its depolarization through all the atrial myocytes, all right? And I say, after the P wave begins, which is, really this rise, about, 25 100ths of a second, the atria will start to contract. But again, this is not showing the actual contraction. The QRS complex is then, we're passing on from the SA node to the AV node, right? So SA node through atria, AV node through AV bundle, through the right and left bundle branch and Purkinje fibers, and somewhere about this point, then the ventricular cells start to depolarize, all right? And ventricular contraction should then begin somewhere right about the R. But again, this graph is not actually showing you the contraction, it's showing the electrical potential and the changes in it, all right? The heart has to reset, so this is our T wave, all right? And you'll notice here that the heart is not electrically excited for a period of time, okay? So there's a point in which we are in the relaxing and we're not going to get stimulated again, that refractory period. So contractile to, so contract, right? and begin relaxing and remain relaxed until we contract again. So this is the nodal system from SA node all the way through Purkinje fibers, and then resetting, and then waiting again until the next stimuli or spontaneous depolarization of that SA node. All right, so again, the T wave shown here is really the reset of the ventricles. The atria reset somewhere in here, but you can't see the electrical changes because of the QRS complex. All right, so say here the ventricular repolarization, marked relaxation, and the inability to respond to another action potential known as the refractory period. All right, so we're going to keep. And as I mentioned, the atrial repolarization occurs during ventricle depolarization. All right. So the cardiac cycle then is, of course, putting this electrical excitation together with the contraction and watching the movement of blood because of contraction. All right. So the formal term is we're starting and continuing blood flow through the heart from one contraction to the next, driven by pressure, which is caused by electrical changes. Our atria are considered primers, so they're going to help, blood is going to come back through them, and then they're going to squeeze and top off the ventricles. The ventricles are power pumps. They are really going to generate the major force and pressure to push the blood through the heart. All right. We need to understand that blood will move out of the chambers, again, during contraction, and this is any of the chambers, and into the chambers during relaxation. So I am going to say, and not for the last time, that the atria and ventricles will be together in diastole, so they can be relaxing together, but they cannot be contracting together. All right? So again, understanding this cause and effect, right? We move from gases, whether it's gases or liquids, things move from areas where there's high pressure to low pressure, and we refer to this difference as the gradient. So when these chambers, right, atria and ventricles are relaxed, blood enters, all right, since the veins have higher pressure, high to low. The AV valves are open, as I mentioned on a previous slide, so blood flows from atria to ventricles. Again, blood is filling in the relaxed state. Action potentials trigger the atrial contraction. So action potentials, again, the SA node spontaneously depolarizing and then exciting all those contractile myocytes in the atria and moving the electrical changes through the atria together. This causes the atria to depolarize, the P wave, and that leads to contractions or systole that will push the blood into the ventricles. The action potential spread through the ventricles, right? So from the SA node to the AV node to the AV bundle, down the bundle branches and up the Purkinje fibers, right? This leads to all the ventricles, or most of them, depolarizing simultaneously, the QRS complex, which will cause them then to contract. And as they contract, they're pushing blood into the arteries. All right, so here's our contractile, right, or cardiac cycle. Ventricular filling in diastole, all right, and I just give you here we go again, ventricular filling. So AV valves, are open between, right? Semilunar valves are closed, as this shows you. Okay, pressure in ventricle is lower than atria. That's why blood comes back into the atria and just moves right into the ventricles. Atrial systole will follow, right, the depolarization of the atrium, as noted by the P wave. So here we see this move into atrial contraction. So P wave, right about here, as depolarization is occurring, we then see contraction. And this would push the blood into the heart. Okay, I'm going to stop here and pick up, can do this on the next video. These are important concepts, so I'm kind of going slow here. So please take your time and ask me any questions.